In this recording, we will be looking at several different examples that use conservation of energy. In the first one, conservation of energy is the entire idea of the problem. And for the last few problems, conservation of energy will be used as the first piece to solve for something, and then the problem will involve projectile motion or it will involve circular motion. In this first problem, there's a pinball machine, and the pinball launcher has a spring with a spring constant of 1.35 newtons per centimeter. Now, the first thing that you may notice is that the units for this are not the correct units for the spring constant. The spring constant needs to be in newtons per meter. So 1.35 newtons per centimeter is 135 newtons per meter. The surface on which the ball moves is inclined at 17 degrees with respect to the horizontal. So this means that when the pinball is shot, it's going to be moving up a certain vertical distance. This problem is going to involve both gravitational potential energy and spring potential energy. If the spring is initially compressed by 2.16 centimeters, so that's 0.0216 meters, find the launching speed of a 0.193 kilogram ball when the plunger is released. So I have this larger picture of the situation happening. So this distance, again, 0.0216 meters, that's the length along the incline itself. The spring constant K was 135 newtons per meter. The first thing that we need to do is pick where the height is going to be 0 for gravitational potential energy. It makes sense to make this lowest point right here where the height is 0. So initially, there will be spring potential energy and there will be no gravitational potential energy. So the initial spring potential energy is 1/2 times the spring constant of 135 times the distance of the spring is compressed, and that is the 2.16 centimeters along the incline. So it's 0.0216 squared. So if you calculate that potential energy, you get 0.03149 joules. The initial gravitational potential energy is 0, and the initial kinetic energy is also 0. At the end, when this is leaving the spring, the final spring potential energy is going to be 0. The final gravitational potential energy is not 0, though. And to find this gravitational potential energy, we need this height. And so just to redraw this to make this a little bit easier to see, along the incline, you have a distance of 0.0216 meters. This is inclined at 17 degrees, so we need this height. So the sine of 17 degrees equals the height over 0.0216, which gives the height when it's leaving the spring of 0.00632 meters. So when looking at the gravitational potential energy, this is going to be 0.193 kilograms times 9.8 times the height of 0.0063. If you do not include this gravitational potential energy, this increase in gravitational potential energy, your speed is going to be too large. If the mass of the ball is not very big, it will not affect your answer very much. But if you do have a more massive ball, this change in gravitational potential energy will be much more important. When we looked at the spring-loaded projectile launcher at the beginning of the year, when we launched it at different angles and from the table, and you needed to calculate where it was going to hit the ground, we made sure that we used the plastic balls. That way, there was not a very large change in gravitational potential energy when we shot it at an angle. The reason that we could not use the steel balls is because this piece is much more important, and we would not have been able to ignore it, and at that point in the year we did not know how to take it into account. So the gravitational potential energy, once we calculate it, is 0.0119 joules. And there's a certain amount of kinetic energy at the end. We can find that amount of kinetic energy by using conservation of energy. The initial potential energy plus the initial kinetic energy have to equal the final potential energy plus the final kinetic energy. Because we have several types of potential energy, this initial potential energy has to be all of the initial potential energies added together, both the spring and the gravitational potential energy. This final potential energy has to be the spring potential energy plus the gravitational potential energy added together. In this problem, one or the other one of them is zero, but if we were looking at when the spring was partially compressed, we would have both gravitational potential energy and spring potential energy that we would need to worry about. So once we plug in those values, our initial potential energy is 0.03149. Our initial kinetic energy is 0. Our final potential energy was 0.0119. And we don't know what our final kinetic energy is. So we can solve for that. 0.03149 minus 0.0119. And we get that the final kinetic energy is 0.01959 joules. Now that's not what the question asked for. The question asked at what speed does it leave the plunger. So that final kinetic energy is 1/2 times the mass. The mass of this was 0.193 kilograms. Times the speed squared. So 0.01959 equals 1/2 times 0.193 times the speed squared. And if you solve that for the speed, you get a speed of 0.4506 meters per second. Again, there was another problem in the notes that we had where we had both spring potential energy and gravitational potential energy. We had the bungee jumper who jumped off of the bridge. This is a similar type of problem. The only difference is the distance that the spring is compressed is not just in the vertical direction. And so you need to relate the change in height of the object to that distance that the spring is compressed using trigonometry. This next problem is a combination of conservation of energy and then projectile motion. So in this problem, a child slides without friction from a height of 10.1 meters above the water along a curved water slide. She is launched from a height 5.8 meters above the water at an angle of 63 degrees above the horizontal towards the pool. Determine her maximum airborne height y above the water. So this is not asking for the delta y that's given in the picture. They want this total height above the water. To do this, we're going to use conservation of energy to figure out what speed she has when she leaves the water slide. And then this becomes a projectile motion problem. So at the beginning, she has a potential energy of whatever her mass is. Her mass is not given, so it's going to have to divide out in the problem, times 9.8 times the height of 10.1 meters. Now what we're doing in this is we're saying that the height equals 0 at the water. Because all of our heights are given relative to that point, that's the most convenient place to pick. So this initial potential energy is 98.98 times her mass. This is not 98.98 meters. The m there is the mass of the girl. The girl is starting at rest at the top of the slide, so her initial kinetic energy is 0. At the top of the water slide, all of the energy is potential energy. There's no kinetic energy. When she reaches the end of the water slide, she's going to have both potential energy and kinetic energy. Neither one of them will be 0. Her potential energy at the end of the water slide is going to be her mass times 9.8 times the height there, which is 5.8 meters. So this gives a potential energy at the end of the water slide of 56.84 times her mass. And the kinetic energy at the end of the water slide, we could solve for that kinetic energy and then use 1/2 mv squared because we need the speed. But for this, since I know that I want the speed, I'm just going to substitute in 1/2 times her mass times the speed squared. And I'm going to be able to solve for that speed directly. So if I use the principle of conservation of energy, again, in this problem, there are no non-conservative forces acting. So the initial potential energy plus the initial kinetic energy equals the final potential energy plus the final kinetic energy. Again, these don't have to be the initial and final points. It's really the potential energy plus the kinetic energy at one point in the motion has to equal the potential energy plus the kinetic energy at some other point in the motion. So her initial potential energy is 98.98 times her mass. Her initial kinetic energy is 0. Her final potential energy is 56.84 times her mass, plus her kinetic energy, which is 1/2 times her mass times v squared. So looking at this, every single one of the terms has a mass in it. So if I divide both sides by m, all of my masses divide out. And if I solve for the velocity, I get the square root of 84.28, which is 9.18 meters per second. Now that's not what this question is asking for. That's the first step in solving this problem. So we know that the girl leaves the end of the water slide with a speed of 9.18 meters per second at an angle of 63 degrees. And she's 5.8 meters above the water. So this is similar to problems that we had earlier in the year where we have a ball that's launched at 9.18 meters per second at a 63-degree angle. From a height of 5.8 meters. And when we did these problems, we needed to find the x and y components of the initial velocity. In this, the x and y components of our initial velocity are not talking about the velocity that she has at the very beginning when she was at rest at the top of the slide, but the projectile motion piece starts when she leaves the end of the slide. And so our initial velocity is the velocity from the end of the slide. It was our final velocity in the previous part. Again, we had this happen. There were several times when we did kinematics problems where we had to break it up into different pieces, and the ending velocity from the first piece became the starting velocity for the second piece. So this is nothing different. So if I find the y component of that velocity, so 9.18 times the sine of 63 degrees, I get that the vertical velocity when she leaves the end of the slide is 8.179 meters per second. The horizontal component, I'll write it down. We do not need it for this part of the problem. There's nothing with this problem that deals with the horizontal distance traveled. That's what we would use this for. Her horizontal component would be 4.168 meters per second. So if I look at the vertical direction, my initial height is 5.8 meters. My final height is what I'm looking for. It's when she goes up. And at this highest point, we know that the vertical component of her velocity is 0. The total velocity is not 0. I could not use conservation of energy to figure out what height she reaches. Again, we would end up going through and we would get the same 10.1 meters that we had before. The reason that we can't do that is because she still does have a horizontal velocity of 4.168 meters per second. If we wanted to use conservation of energy, which would be perfectly valid, we would take the kinetic energy associated with that horizontal velocity that she has, plus the potential energy associated with the unknown height, and that would have to equal the total energy that we had before. So that would be an alternate way of solving it. With this, because we had already broken the velocity into components, the first thing that people usually are thinking about is projectile motion and kinematics. So that's the method that I'll use to solve this problem. So the initial vertical velocity, again, that's the 8.179 meters per second. So that's her vertical velocity as she leaves the end of the slide. The final vertical velocity is 0, because when she reaches her maximum height above the water, the vertical velocity is 0. Her vertical acceleration is negative 9.8 meters per second squared. And we don't know the time, and we're not going to end up using the time. Again, problems like this are very common where you have to use some other method, conservation of energy often, to figure out what the velocity is, and then it turns into a projectile motion piece. Most problems in physics cannot be broken down just into conservation of energy or conservation of momentum or projectile motion. Usually you have several things that are happening. On the AP test, they will have most of the free response problems are going to be problems that involve several different pieces of information. We're now at the point in the year when we're able to do a lot more of the free response problems because we now know enough different areas of physics that we can calculate all the different things asked for in the problem. So to solve this, I can use the kinematics equation that relates the initial and final speeds to the acceleration and the initial and final heights. So the third equation on our sideboard. So we have 0 equals 8.179 squared plus 2 times negative 9.8 times y minus 5.8. Again, we have to take into account that she was starting 5.8 meters above the water already, and they want the total height above the water. So we need to have that included. So if you solve that for y, you get that her final height above the water is 9.213 meters. And this is what the question asked for. So go back and double check. So determine her maximum airborne height y above the water. So that is what we just solved for. Her maximum airborne height is going to be the height that she has when the vertical component of her velocity goes to 0. But we're only looking at that vertical component going to 0 after she leaves the end of the slide. And when she's moving on the slide, it's a conservation of energy problem. So anytime you see something where you have someone sliding down a curved surface, so it's not something that's just an inclined plane, the first thought that you should have is to think about conservation of energy. And then, because we have something being shot with a certain velocity and we're looking for a height, then the next thought that you should have is to use kinematics and the idea of projectile motion. This next problem is similar to a few different problems that are in the homework. It's also in some ways similar to that last problem that we just did, where it's a projectile motion piece plus a conservation of energy piece. So in this problem, a block is pushed against a spring that has a spring constant of 5.6 kilonewtons per meter. So again, this is not the standard units, so that has to be 5,600 newtons per meter. It compresses the spring a distance of 5 centimeters, so that's 0.05 meters. The block starts at rest, it's accelerated by the compressed spring, and it slides across a frictionless track. But it encounters a rough patch. So there's going to be friction, and we're going to be including the work done by friction. We have a non-conservative force acting here. It leaves the track horizontally, flies through the air, and subsequently strikes the ground. The first question that's asked is, what is the speed of the block when it leaves the track? So to solve this, the most common thing that people might do might be to set the height equal to 0 down here. And this means that at the beginning, I'm going to have spring potential energy and gravitational potential energy. But when it goes to the edge of the track and it's moving with some unknown speed there, the gravitational potential energy does not change. And so if I wanted to, I could make the gravitational potential energy 0 at that point. But because most people usually would take the lowest point to be where the gravitational potential energy is 0, I'm going to include both types of potential energy and show that the gravitational potential energy just subtracts out. Something that's important is this mass right here is given in grams, so that needs to be 0.451 kilograms. So at the beginning, I have some potential energy stored in the spring. It's 1/2 times 5,600 times 0.05 squared, which is 7 joules. The initial gravitational potential energy is 0.451 kilograms times 9.8 times the height of 2.4 meters. Which gives a gravitational potential energy of 10.608 joules. The initial kinetic energy is 0. The block is compressed up against the spring and it's not moving. As this block is sliding along and it leaves the edge of the track, there's no spring potential energy because the spring is not compressed anymore. The final gravitational potential energy is still going to be 10.608 joules because it's still at a height of 2.4 meters. The final kinetic energy is 1/2 times its mass, 0.451 kilograms, times the speed squared. But there's a little bit more that I have in this problem because I have to take into account the work done by friction. If I look at that block sitting on the surface, the block has a weight of 0.451 times 9.8. So its weight is 4.42 newtons. Because the surface is flat, the normal force just equals the weight. So it's 4.42 newtons. And I can calculate the force of kinetic friction. The force of kinetic friction will be the coefficient of kinetic friction times the normal force. So that's the 0.3 that's given in the problem for the coefficient of friction times 4.42. Which is 1.326 newtons. The equation that I have for conservation of energy when there are non-conservative forces acting is that the initial potential energy plus the initial kinetic energy plus the work done by the non-conservative forces, such as the force of friction, have to equal the final potential energy plus the final kinetic energy. So what we have, there's a certain amount of total energy at the beginning. The non-conservative work is either adding to that energy or it's taking energy away. In this case, the friction is acting against the motion of the block, so it's going to be taking some energy away. And then our final mechanical energy at the end is going to end up being a smaller quantity. So if I plug in the values, my initial potential energy has to be the 7 joules for the spring that I have plus the 10.608 joules that I have for gravitational potential energy. There's no kinetic energy at the beginning. And then the work done by friction, first of all, it's going to be negative because the force of friction is against the motion. And it's going to be the force of friction, 1.326 newtons, times the horizontal distance of 1.2 meters. And this is going to equal the final potential energy, which again is the final potential energy of the spring, which is 0, plus the final gravitational potential energy, 10.608 joules, plus my kinetic energy, which is 1/2 times the mass of 0.451 times the speed squared. So again, this was the final spring potential energy. This was the final gravitational potential energy. You'll notice if I subtract 10.608 from both sides, the gravitational potential energy goes away. I could have called my initial height 0, and it would not have changed anything about the problem. So if I do this, I have 7 joules minus my work done by friction, which is 1.451 0.5912 joules, and that equals 1/2 times 0.451 times the speed squared. So if I solve for my speed, I get the square root of 23.986, which is 4.898. So the speed that this leaves the cliff with is 4.898 meters per second. And this is something that's only moving horizontally initially. And so now for the rest of the problem, it becomes a projectile motion problem. What is the horizontal distance, x, that the box travels in the air? To do this, we look at our horizontal motion. The initial horizontal position is 0. The final horizontal position is what we're looking at. The initial horizontal velocity is the 4.898 meters per second that we just found. The horizontal velocity stays constant because there's no horizontal acceleration. And we're going to need to solve for the time. If I look at the vertical motion, it starts from a height of 2.4 meters. When it reaches the ground, it's at a height of 0 meters. The initial vertical velocity is 0 because the block is only moving horizontally when it leaves the cliff. The vertical acceleration is negative 9.8 meters per second squared. Again, I need to find the time. So again, we did these problems a lot at the beginning of the year. This was the method we used to find the initial velocity of our spring-loaded projectile launcher. We used the vertical motion to calculate the time, and then we used that time with the horizontal motion to find the horizontal distance. So looking at the vertical motion, we use the second equation. So we have the final height of 0 equals 2.4. The initial velocity is 0. And 1/2 times negative 9.8 times t squared. So we get the time in the air is 0.6999 seconds. And so the horizontal distance is going to be the horizontal velocity of 4.898 meters per second times the time of 0.6999 seconds. And in the horizontal direction, there's no acceleration, so it's just the horizontal velocity times the time. And for this, we get that the horizontal distance traveled by the box is 3.428 meters. Okay, the third part. What is the total speed of the block when it hits the ground? Because we've been doing this problem, this middle part, we did using kinematics. The most common thing that people would think of to do this would be to use kinematics to find the speed. And so I'll first do it that way, and then I'll show the other way that we could do this using conservation of energy. So when it hits the ground, we know that the horizontal velocity is still going to be 4.898 meters per second. The vertical velocity is going to be the initial vertical velocity plus the vertical acceleration times the time. But that's 0 because it was not moving vertically at the beginning. The vertical acceleration is negative 9.8. The time we just calculated was 0.6999. So that vertical velocity is negative 6.859 meters per second. The negative sign is just the fact that the velocity is moving downward. I don't need to include that negative sign because I've drawn my arrow pointing downward. And so to find the speed is the total of the x and y components put together. It's the magnitude of the velocity. And so you would get that from the Pythagorean theorem. It would be 4.898 squared plus 6.859 squared. And you would get a speed of 8.428 meters per second. So that would be perfectly fine. If you wanted to use conservation of energy, we could go through from the very beginning of the problem, where before it has reached the friction patch, or we could look at what its velocity was after it reached the friction patch. Either way, it doesn't matter. I'm going to look at what happens after it hit the friction patch. And so you have this object, and it's traveling with the horizontal velocity that we had before of 4.898 meters per second. Our gravitational potential energy that it had was 10.608 joules. And again, we had calculated that up here. That was the mass times 9.8 times the height. The kinetic energy is 1/2 times the mass. Again, we had that up here. So the mass was 0.451 times 4.898 squared. And when it reaches down here, it has a certain speed v. It's at a height of 0. So the final gravitational potential energy is going to be 0. And the final kinetic energy is 1/2 times 0.451 times the speed that we're looking for squared. So again, if I use this method, this is after it hit the patch of friction. So I just have to look at the initial potential energy plus the initial kinetic energy. Is that equal to the final potential energy plus the final kinetic energy? This is after it has left the spring, so there's no spring potential energy. I'm just leaving out of the equation. So we have the 10.608 joules of potential energy that it has, plus this kinetic energy up here was 5.41 joules. And that equals the final potential energy of 0 plus 1/2 times 0.451 times the speed squared. So if we do 10.608 minus 5.41 times 2 divided by 0.451, and we take the square root of that. Sorry for the delay. I accidentally subtracted the 5.41 from the 10.608 when I calculated it. I knew that the answer that I had gotten was incorrect. So when I use this method, if I do 10.608 plus 5.41, I apologize if I might have said that you subtracted. So 10.608 plus 5.41 joules, and that equals 1 half times 4.51 times v squared. If you solve that for v, you get 8.428 meters per second, which is the answer that we had just found up here previously. So either way, either method would be okay for solving this. So again, this is the same as up here. It doesn't matter which method you use. You can either use conservation of energy or you could use kinematics. Because you already had everything set up for kinematics, it would make the most sense to use kinematics. But if we hadn't gone through and calculated that time that it was in the air already, and if we hadn't used that to find the horizontal distance that it traveled, if we hadn't done all of those things already, if all it wanted was what the speed when it reached the ground was, the conservation of energy method might be the method that's a little bit easier. It would be 1 or 2 steps shorter. If the kinematics method is the first method you think of, then definitely by all means use that method. They both give the same value. The last problem that I want to look at is one that involves circular motion and conservation of energy. And so this is similar to one that we had looked at in the notes. This is also similar to a couple of different problems that are on your homework. But this problem, everything is going to be solved in terms of variables. So in this problem, we have a loop-to-loop system where the radius of the loop is capital R. A small block of negligible size. So that means that we don't have to worry about the fact that the drawing is a square block. It's going to make all of these turns okay. It's not going to tumble over. So a small block of mass m is released from rest at point P, which is at a height of 4 3/8 r, or that's 35/8 r. So the kinetic energy at point P at the top is 0 because it's released from rest. The potential energy at point P at the top of this track is m times g times the height, which is 35 r over 8. So that's 35/8 mgr. If I want the kinetic energy at B, so to do this, I was saying that the height is 0 all the way down at point A, at the lowest point in the motion. At point B, this height is capital R. So if I'm looking at the kinetic energy at B, first, the potential energy at B is the mass times G times R. And so if I use conservation of energy, the potential energy at point P plus the kinetic energy at point P has to equal the potential energy at point B plus the kinetic energy at point B. I have 35/8 mgr plus 0 kinetic energy equals mgr plus the kinetic energy at B. And so if I subtract mgr from both sides, I get that the kinetic energy at point B is 27/8 mg capital R. Again, that's all the question was asking for. It was asking for the kinetic energy at B in terms of these variables. This was a multiple choice question that I had taken from the homework, and so this would have been one of the answer choices that was there. If I want to find the tangential speed at point C. So the tangential speed is the speed that's tangent to the circle. So that's the speed that we would be finding most times. So to do that, the potential energy at point P plus the kinetic energy at point P has to equal the potential energy at point C plus the kinetic energy at point C. Again, point C is at a height of 2r above where I called the height equal to 0. So I have 35 eighths mgr plus 0. Again, I could have used point B as my starting point. If I would do mgr plus 27 eighths mgr, so that's the total energy at B, that still is 35 eighths mgr. That's the idea of conservation of energy. If there are no non-conservative forces acting, the potential energy plus the kinetic energy at any point equals the potential energy plus the kinetic energy at any other point in the motion. So with this, the potential energy at point C is mg times the height of 2r. And instead of just leaving this as the kinetic energy at C, because it's asking for the tangential speed, I'm going to substitute in 1/2 times the mass times the speed at C squared. And so if I subtract 2 mgr from both sides, again, that's 16 eighths mgr. So 35 eighths minus 16 eighths is 19 eighths mgr equals 1/2 m times the speed at c squared. I can divide both sides by the mass. So the mass is not going to matter for this problem. You're going to have the same speed no matter what the mass is. And so if I multiply both sides by 2, I get 19gr over 4. Again, multiplying by 2 instead of dividing by 8, I'm dividing by 4. This equals v squared. So this means that the speed at point C is given by the square root of 19gr over 4, or it would also equivalently be the square root of 19gr, that quantity over 2. Again, this is why it's important that if you're writing this out, if this was on the AP test, you make it clear what things are underneath the square root and what things aren't. Because if you have the square root of 19gr divided by 4, and the 4 is not inside the square root, then that's a completely different answer. Find the force NA, so it's the normal force at point A, with which the track is pushing up on the block at point A, which is at the bottom of the loop. So just looking at this, this is at the bottom of the loop. Loop is radius r. You have the block sitting there, and you have the force down is the weight. The force up is this normal force. And in this problem, the net force is not 0. This is moving in a circle. So the net force must be the force towards the center of the circle, which is that normal force. And then I add my other forces. Any forces away from the center of the circle, I make negative. This net force also equals the mass times the acceleration. So that's m. The acceleration is given by the speed squared divided by the radius. And so the first thing that we need to do is we need to find the speed at point A. To find the speed at point A, I can look at any point in the motion. So if I look at point P and point A, so my potential energy at the beginning was 35/8 mgr. There was no kinetic energy. And then at point A, there's no potential energy. 1/2 times m times the speed at A squared. And so this is going to give me 35 mgr over 4 equals m times the speed at A squared. Divide both sides by m. And I get that the speed at point A is the square root of 35 gr over 4. Again, everything is underneath the square root. Because in my net force equation I want v squared, I really didn't need to go that last step. So this net force is going to be m times 35 gr over 4, because that's the speed squared, divided by the radius. So putting those things together, the upward force of the track at point A minus the weight is going to equal 35 mgr over 4r. So the r's divide out. I need to pause for a second. Sorry. Okay. Excuse me. I had a cough that I needed to take care of. So the r's cancel out. And so solving this for that normal force, I get that the upward force of the track at point A, if I add mg to both sides, I have 35 mg over 4 plus mg. So it's going to be 39 mg over 4. And the main reason I want to work through an example like this is because it's very common for you to have to work things out in terms of variables on the free response section on the AP test. So I want to make sure that you would understand how to do that. Okay. For this last part, the block does not begin at the height of 35r over 8. So we're going to find the minimum speed of the block at point C so that it can pass by the point without falling off the track. If you look back into the notes, we had done something similar to this. So when it's going around the track, at point C, you have its weight pulling down. You also have the track pushing down. If I look at those things together, both of those forces are in towards the center of the circle, so they're both going to be positive. So the net force is going to be mg plus the force of the track. And the net force also equals m times the speed squared over the radius. If we're looking for the minimum speed, that's when the force of the track goes to 0. In your homework that you have something that's going over the top of a hill. And so in that case, that's looking for the maximum speed that you can have before it leaves the track. But in either case, the minimum speed when it's going under the underside of a track or the maximum speed that it has when it's going over the top of a loop, they're both going to be at the same spot. They both happen when the force of the track goes to 0. So if we set mg plus 0 equal to m times the speed squared over the radius, and we divide out the m, we get that the speed is the square root of rg, which in your homework you'll notice that the maximum speed that you can have when you go to pass the top of the track, that's the same speed. Um, you're solving things very similarly. So to figure out the minimum height of the block at point P so that it can pass by point C without falling off the track, we're going to say the potential energy at point P, so it's the new point P, so it's not mg times 35/8 r. So it's the new potential energy at P plus the new kinetic energy at point P, and that's equal to the potential energy at point C plus the kinetic energy at point C. Again, the potential energy at point C is not zero. We calculated it. It was mg times 2r. So if we have m times g times my minimum height that I'm looking for, it's starting from rest at that point. This was mg times 2r. And the kinetic energy that I have here is 1/2 times the mass times the square root of rg squared. So if I solve this, I get mg times the minimum height equals 2mgr plus 1/2 mgr. So the first thing that I can do, I see that I have an m and a g in every term, so I can divide everything by mg. And I get that the minimum height is 2r plus 1/2 r. So that's going to be 5/2 r. And again, you can look at these to see if the answer makes sense. If we're looking for a height, it needs to be some number times some other length. R is the radius of the circle, so 5/2 r is also a length. Hopefully, these problems will help as you're trying to do some of your other homework problems. These are some examples. There will be more examples that get added, but this is just some of the different types of problems that involve conservation of energy and other types of motion.